Well, with the viewpoint of the linearizing at the working point, we will be able to discuss a more general problem. In this problem, we have a small signal superposed with a DC. The small signal can be interpreted as a signal that will be amplified. It can also be understood as a disturbance of the DC source. This is a linear resistor and a voltage-controlled nonlinear resistor. Now we solve it by the analytical method. In the case of the disturbance, we define the current of the whole circuit as I0 plus delta IT. We define the voltage of the nonlinear resistor as U0 plus delta UT. U0 and I0 refer to the working point under the excitation of Us alone. Recall such a working point just now. It is a concept of U0 and I0. Okay, we write the equation of the whole circuit. We need to write a KVL equation. So it is Us plus delta UST equals R times I0 plus delta IT plus U0 plus delta UT. This is the equation we can get. In addition, we also know that for the nonlinear resistor, I0 and U0 are its working point. So we have I0 equals GU0. For the nonlinear resistor, the voltage across it is U0 plus delta U, and the current flowing through it is I0 plus delta I. There is a nonlinear relationship between them. We write the nonlinear relationship, that is I0 plus delta IT equals GU0 plus delta UT. It is a nonlinear relationship if we can ignore the items of the second and higher derivatives. It can be written as GU0 plus G prime U0 times delta UT approximately. Here G prime U0 refers to the slope at that point. Okay, because I0 equals GU0, we knew it at the very start. According to the equation, we can get I delta IT equals G prime U0 times delta UT. Substituting the result into the fundamental KVL equation, we can find that this equation can be divided into two parts. The first part is a question for solving the DC working point. That is, Us equals R times I0 plus U0. It is these items. Here, I0 and U0 keep a nonlinear relationship. This is the first part, the circuit solving the working point. Apart from this, we find that there are such a pile of items. We can write them down as delta UST equals R times delta IT plus delta UT. In addition, we can also write the small signal relationship. That is, delta IT equals G prime U0 times delta UT. We need to make a description for the G prime U0. It means the value of dG over du at the time of U equals U0. So if you have determined U0, then the G prime U0 is also a known value. Look at this group of equations. They are nonlinear algebraic equations. While this set of equations are linear algebraic equations about delta UT and delta IT. It is very important. It has realized one thing we presented in page 2 of this lecture. That is to say, we can use a small signal to realize some special functions For the circuit or equation containing the small signal, it is a linear relationship between the excitation and the response. It is very easy to use the node method, the loop method, the superposition, and the Thevenin to analyze and design. Okay, it was a pure mathematical deduction just now. Let's turn to the circuits. Look at the equation on the left. We wrote it just now. It's a nonlinear algebraic equation for solving the working point. We might as well draw the corresponding circuit of this algebraic equation. What kind of the circuit should it be? Very good. It should be such a circuit. Right? For this circuit, we get this equation by the KVL and get this equation by its relationship. The working point is U0, I0. Even more important for the linear algebraic equation about delta IT and delta UT on the right, based on the circuit, how to get its corresponding circuit? This equation is also a KVL equation, so we can write like this. What is it so as to make it delta UT? What's the relationship between delta IT and delta UT? Right, it is equivalent to a linear resistor. Its resistance is 1 over GD. In the next lecture, we'll give you a detailed analysis for the common circuit component. What is the corresponding small signal model? With this tool, we can analyze the small signal circuits conveniently. Before finish this lecture, I have a question for you. For such a circuit containing two excitations, we divide it into two circuits, each with a source. And we know clearly the sum of their effects are the branch variables IT and UT of the circuit. My question is this the superposition method?